We'll get going with the introductions. Welcome to SGP's Strontium Isotopes Proxy Primer. For those of you who aren't familiar with us, we're a research consortium that's aiming not only to build a large database of geochemical data, but figure out how we can come together as a community to learn how to analyze sedimentary geochemical data through Earth history better. And this Proxy Primer series is part of that. We're coming up on our phase 2 data release. This will be coming out in February 2025, which has been built by greater than 200 scientists around the world. And so if you're interested in joining, please get in touch with me or check out our informational or search website. The Proxy Primer series itself is aiming to accessibly explain the basics of a geochemical proxy or some other sort of geological or stratigraphic method to a broad audience. Especially to people that may not necessarily be intimately familiar with it. For me, personally, strontium isotopes is one of those things that I felt like I must have just been absent the day they taught about it, because I've somehow never managed to really learn that much about it. And so I'm really delighted today to have this opportunity to learn from two of the world's experts. These Proxy Primer videos are then curated on our YouTube channel, so people can keep using them as educational resources. And our other goal, which we'll do at the end of this talk, is to turn off the video recording and have a open space for interaction with the experts on each proxy. So far in 2024, we've had proxy primers on uranium isotopes, Bayesian approaches to stratigraphy, and today on strontium isotopes. Looking ahead to 2025, we're looking forward to talks on paleosalinity proxies by Dr. Tom Algeo, and ideally something on care principles for indigenous data governance. So today, I'm delighted to introduce, as I said, two experts on strontium isotopes who are going to be tag teaming this talk from UCL. The first is Dr. Ying Zhou, who did her undergraduate and master's degree at Nanjing, before moving on to her PhD at University College London, and is now currently a lecturer at Johannes Gutenberg University in Mainz, while also retaining an association with UCL. The second person is Dr. Graham Shields, also at UCL. He's originally from the UK and did his undergrad at Imperial College before heading off on an extended tour abroad, doing his PhD at ETH Zurich, and then a number of posts. I have to look at my notes because they're a globe-trotting trip through France, Canada, Australia, and Germany before coming back to UCL in 2007, where he's remained ever since. And so why don't we jump into the Proxy Primer?
Okay, right. So if I can work out which one it is. It's that one, isn't it? Is that right? Can you see that?
Yeah, but it's in the it needs to go into the other.
You need to help me here because it's your desktop. Is that the right one?
Just to change.
Just Freigabe stoppen, ne? And then we go back, you choose the right one, because I'm not even sure which one it is. In here. Ah, it's that one, okay.
Okay, this one. Okay. So now you have to don't do that. You can do this. And then you do Bildschirm 2, Freigabe. Can you see it now? And?
No, because that's your desktop, isn't it? Yeah.
There we go.
Perfect.
That's perfect. Okay, great. Okay, it's a bit difficult with multiple screens. So sorry about that. So without further ado, let's get into this. Let's get in. Sorry, what happened there? I've done it again. Oh boy, you have to help me again.
Just use this. Oh.
Because of the multiple screens, I'm a little bit confused. I just go here for the screen. Which one?
Oh, have you stopped?
No.
Okay.
So you can see everything, right?
Yeah, well, so the view looks good now.
Okay, yeah, okay. I've never.
I think you just need to be able to advance.
Yeah. All right. Yeah, it's difficult to do two things at once. It seems. Okay, so this is going to be a basic introduction to strontium isotopes. So that's why we call it a primer. So it perhaps will be a little bit too basic for some people, but hopefully we'll get into some of the meat later on and start to sort of understand how this particular curve, this is from the geological timescale book 2020, how it was created and how we can also interpret some of the features on it. As we go through, you'll see some of the contents come up in bold, so you know pretty much where we are. So let's just get straight into strontium as an element. Strontium has four naturally occurring stable isotopes, 88, which is the dominant isotope, 87, 86, and 84. You may also hear about other isotopes like 90 strontium, which is a product of nuclear fission and has been with us since the great acceleration of the 1950s. And a few of its isotopes, its radioactive isotopes, are used in medicine. We're particularly interested in 87 strontium for the purpose of this talk. And that's because 87 is a radiogenic product of radioactive decay, beta decay of 87 rubidium. And therefore, the 87-86 ratio of natural materials can vary, and not simply due to fractionation, but simply due to the mixing of different sources of different age and rubidium-strontium ratio. Strontium isotopes are reported in three different ways. You'll see this in the literature. The most common way would be 87-86, and we will focus on this today. You will often see 87-86 also expressed as epsilon strontium. So epsilon normally in geochemistry means parts per 10,000, whereas delta means parts per 1,000. So you'll see epsilon strontium as a per 10,000 deviation from some standard or background or baseline. The baseline normally is taken as mantle or bulk earth. And so epsilon strontium would be a deviation from the contemporaneous mantle. I'm not going to show any of the epsilon strontium today, but it's just worth noting that that also exists. When we measure 87-86 strontium, we normally cancel out the natural fractionation and fractionation within the instrument. We call that mass bias. And therefore, we can't actually normally get the stable isotope fractionation. These days, we can do that by double spikes and various techniques we'll come back to. But we're not going to go into this too much today. But there we get something called delta 88 strontium, which is a deviation of 88 over 86 relative to a standard. So today we'll mostly focus on 87, 86. There's already quite a lot to say just about that. So strontium, I think, is one of those sort of conventional isotopes that seems to have been around for a long time. There was a lot of pioneering work, especially in the 1950s, as with sulfur, as with oxygen, carbon, and there we have strontium. So the very first time that I can think of that we first had an account of fluctuations of 87-86 in seawater, and that was assigned to the rocks undergoing weathering, so material which is dissolving and going into the ocean. That was gas 1955, so very early on. There were some early attempts to actually make a curve. So Peterman et al. 1970 would be a key point in time, but it was in 1982, I suppose, that we got the very first fairly complete idea of secular variation of seawater 87-86 strontium, and that was a paper by Burke et al. 1982, very much driven by the petroleum industry. And from that point on, we could start using strontium isotopes for stratigraphy, for correlation, and also for dating. So before we get into strontium isotope stratigraphy, shortened to SIS, what are the basic principles behind what determines the strontium isotopic ratio of materials? So as I said, we're not really dealing with isotopic fractionation here. We're simply dealing with the different strontium isotope ratios of natural materials and the mixing of those sources. So this is all to do with radioactive decay. And the half-life of 87 strontium, rubidium is 10 times as long as the age of the solar system. So it's only a proportion of that 87 strontium, which is actually a product of decay because of its such long half-life. So we can sort of draw that straight line relationship, that isochron here, and we can see that in sort of isochron space. As you go along time, this line, this isochron will get steeper and steeper, and that gradient is approximately e to the lambda t minus 1, where that's the radioactive decay constant and the time. So this is dependent, this slope is dependent on the age. So to cut a long story short, the strontium isotopic ratio of the material is really dependent on two things. Firstly, its age. So with time, the radiogenic strontium should build up in the material, and also its rubidium-strontium ratio. The more rubidium there was to begin with, the more radiogenic strontium you will have. So we can actually use the rubidium-strontium system as we would any other radioactive decay chain as a geochronometer. And if we had a series of materials with relatively high rubidium-strontium ratio, they should fall on this line of equal age and should cross over along the y-axis at the input value. So that's the theory, at least. So as long as they were all starting with the same medium, they should fall along this isochron. So, but to keep it simple, really, we just the strontium isotope ratio is dependent on the age and the rubidium-strontium ratio that it started with. Okay. What determines the rubidium-strontium ratio of a rock? Well, it depends on its geological history, and it depends on the history of extraction from the mantle, essentially, the formation of then depleted mantle, the extraction of more felsic magmas, and those processes. With those processes, we talked about things like incompatibility and compatibility. So rubidium is what we'd call a large iron lithophile. So here is on the left. It's a larger iron than strontium, and large iron lithophiles tend to accumulate in the felsic melt. So they tend to be accumulated in things like granites and the upper continental crust. And it leaves behind strontium preferentially. So the rubidium-strontium ratio of the extracted evolved melts will tend to have a high rubidium-strontium ratio. So rubidium is preferentially enriched in the continental crust relative to the mantle. So we can see that pictorially here in this great diagram from Bill White, and you can see without too much imagination. So continental crust is enriched in these large iron lithophiles. So there we are, rubidium. There's a lot more rubidium in the continental crust than in the bulk silicate earth or in the average mid-ocean ridge basalt. And it leaves behind what we call the depleted mantle, which is depleted in rubidium. And then strontium likewise is not quite as differentiated. And so therefore, over time, as you extract melt into the upper continental crust and you start recycling that, the rubidium-strontium ratio will be higher in the continental crust than in the mantle. And that will lead, therefore, then to different paths of strontium isotope evolution that we'll get to in a moment. You can also look at this in terms of the Bowen reaction series. So as we get from ultramafic to felsic rocks, we tend to have minerals which are more enriched in rubidium than in strontium. And so they will have, over time, increasingly divergent and more radiogenic strontium isotope ratios. So clearly, things like micas Clay minerals that contain potassium will have a lot of rubidium, and therefore they will be highly radiogenic. And over time, they will become increasingly radiogenic and will diverge from their parent material. So over time, we actually have an increasingly divergent pattern of strontium isotopes from the solar system initial value, which we can sometimes see in meteorites. The mantle evolves only relatively slowly. And as we get the depleted mantle, that rate of increase of radiogenic strontium starts to lessen. And then at some point through time, we also have a divergence to high rubidium strontium crust. And here it's drawn as a straight line. But in actual fact, it could be quite complicated depending on which model of the crustal evolution that you want to choose. So that could be a little bit more complicated than is shown here. But I guess the basic principle is that the crust and the mantle will diverge increasingly over time. And those are the two main contributors to seawater strontium. So that's why I'm spending a bit of time to talk about that. So then what controls seawater strontium? Well, a lot of it will depend on the weathering of that rubidium enriched radiogenic crust. And here we can see, unsurprisingly, that there is a reasonably good relationship between the strontium isotopic ratio of the dissolved load, which is going into the ocean, and the age of the bedrock, which is undergoing weathering. And as I said, that's largely because with time, the rubidium strontium, the strontium isotopic ratio will increase. So the older the rocks, the more radiogenic that dissolved input will be. So we can integrate all those sources. So looking at the volume of material coming into the ocean and their isotopic ratio. And so most estimates end up with something around 0.7011 as the riverine load. Okay, so that's sort of our end member in terms of the radiogenic end member. We're weathering rubidium enriched continental crust. And that's bringing in strontium. The river runoff is 4.7 times 10 to the 10 moles per year. A word of caution, however, there are some unknowns here. This is clearly the dissolved load that you can measure in rivers, but you also have to think that 30 times more strontium is actually coming into the ocean as detrital load. And we're quite unsure of how much of that may desorb once it gets into estuaries and gets into the open ocean. And there are papers like Ulcus et al. 2012 that suggest that that fraction is quite significant. And so this may be showing us a slightly biased picture. If we put that into a whole diagram to explain schematically the major controls, so we have the riverine input here, which is the radiogenic end member, bringing in this sort of along this orange line, radiogenic strontium, but we also have hydrothermal exchange, which is bringing through this red line strontium, which is unradiogenic. So that's sort of our other end member. We call that the mantle input, as opposed to the continental crust input, but it's essentially rivers bringing in their load, some of which are not radiogenic. They could be relatively unradiogenic, depending on what they're weathering, but in general, it's radiogenic, and hydrothermal exchange. So that's strontium from seawater, which is entering into hydrothermal cells, and when it comes out of those cells, it's exchanged its strontium with the unradiogenic ocean crust. And so that's bringing in unradiogenic strontium. So you can look at this is the Phanerozoic curve, sort of a schematic version of it through the whole Phanerozoic, 500 million years of ups and downs. You can see it as showing the relative proportion of a terrestrial or continental crust or riverine input relative to ocean crust or mantle input. And so people have often interpreted the strontium isotopic evolution of seawater in terms of things like seafloor spreading rates. So that's the hydrothermal exchange, or in terms of the continental crust weathering rates. Also on this diagram is a buffering factor from limestone, because calcium carbonate is continually being formed and redissolved, and so that will to some extent buffer the strontium isotopic composition of seawater. If we look at this over a long period of time, and I do apologize that in some of these that time is going from left to right, and some is going from right to left. So here we're going, today is on the right-hand side. You can see unsurprisingly that our best idea of the strontium isotopic evolution of time, I say our best, but this is 20 years old now, it should actually fit between these two end members. And the first end member is the riverine flux, which is red, and then the mantle input is also in red here, and the seawater curve sits somewhere in between. And of course, as you go back in time, it gets a little bit less clear. What we also have on here is an idealized silicate weathering flux, and an idealized carbonate weathering flux, because I think it's important to realize that most strontium coming into the ocean today is actually from limestone weathering. And we have a fairly good idea of the composition of that limestone, because we know the average age of rocks undergoing weathering. And we know the isotopic composition of past oceans, so we can kind of reconstruct to some extent the isotopic composition of carbonate weathering. So if we take sort of the ideal silicate weathering flux and the ideal carbonate weathering flux, so we can recreate sort of an ideal riverine flux. But this is ideal, this is not, none of this is actually measured, and so a word of caution it needs to be applied here. So using that, we can then see, well, over time, so at what time was the strontium isotopic composition of seawater much closer to the idealized riverine flux, and therefore much further away from the mantle input, and at other times it was much closer to the mantle input. And if you sort of normalize that, you can have a curve, an idealized curve of river runoff versus mantle influence. You know, basically when the values are low, these are almost like supercontinent cycles. These are times of supercontinent tenure. So very low erosion rates, peneplanation, and then also rifting. So the exposure of volcanic rocks, which are unradiogenic. And then on contrast, you have peaks like this in the Cambrian, the Ediacaran Cambrian, where we are dominated, it appears, by riverine flux. And that's related to the high runoff from these eroding mountains. However, looking at this, we don't know whether this is due to weathering rates or whether it's related to the isotopic composition of material undergoing weathering. The second is more likely, and we will come back to that. Other things to consider in general terms is the isotopic homogeneity of the ocean. So we normally assume when we do strontium isotope stratigraphy that the oceans are homogeneous, at least as far as we can measure, so to about 5 or 6 decimal places. And that's because strontium has a very long ocean residence time. So when you look at the concentration of strontium in the ocean compared to how much is coming in through rivers and how much is coming in through hydrothermal exchange, strontium sits around an ocean for a very long time relative to the ocean mixing rate, which is 3 orders of magnitude shorter. Strontium is therefore a conservative element. It co-varies linearly with salinity, is about 8 milligrams per liter. But there's variability in strontium concentration with depth or with from basin to basin. So that's to do with various different currents, but it's also to do with the fact that certain organisms like acantharians, they build their shells these days of strontium sulfate, and they tend to dissolve with depth. So there's some variation in strontium and strontium calcium ratio, but there isn't really much variation in terms of strontium isotopic ratio. And that's what this table shows, which is looking at shells, seawater, and comparing them. And to a rough approximation, they're pretty much the same. In order to compare data from lab to lab, we normalize usually everything to this standard, and that's been the case for many decades now. However, some people do suggest that there may be isotopic homogeneity. So this is one such study where you can see there is a significant difference in this particular case between Indian Ocean seawater and lots of different samples and different depths of Atlantic Ocean seawater, and that potentially relates to this strontium cycle that I was referring to. But to most intents and purposes, this is only in the 5th or 6th decimal place, and this is often beyond what we can actually measure, especially in the geological record where there are many other sources of potential poor reproducibility. Okay, so which proxies then do we use? We can't measure directly seawater, so we have to use proxy materials. And again, I will show this relative to other proxies, other of these conventional proxies, but essentially we can use very similar ones. Biogenic carbonate is preferred, of course, in the Phanerozoic when we have shells. And we can determine if those shells are well preserved or not, or whether they were made of a metastable mineral which is subsequently recrystallized. So if it's well preserved, biogenic carbonate is the go-to proxy material. But for much of Earth history, we were actually forced to look at whole rock. That could be all different forms of carbonates, like dolomite, even early diagenetic cements. But there's also apatite and barite that can also be useful. So that's sort of saying the same thing. Anything which is a orthogenic mineral precipitated from the open ocean can potentially give us the contemporaneous isotopic value of seawater. And here's the various different preferred biogenic carbonate sources. So in relatively young samples, foraminifera is a good choice because it's made of low magnesium calcite, which is not metastable. And if it's well preserved, it probably hasn't undergone any recrystallization. Belemnite similarly started off life as low magnesium calcite. Aragonite, of course, will eventually revert to low magnesium calcite. So aragonite tends not to be the go-to carbonate form for strontium isotope stratigraphy. Conodonts also are possible. They are quite strontium rich due to their apatite mineralogy, and I'll talk about that in a moment. Oops. And then for a lot of Earth history, we are reliant on bulk rocks. So how much strontium actually is in a carbonate mineral? Well, that depends on the distribution coefficient. So different minerals incorporate strontium in different ways. So it really depends on their mineral structure. So if the distribution coefficient is greater than 1, then the strontium-calcium ratio in the mineral will actually be higher than in the ambient fluid in seawater. If the distribution coefficient is less than 1, then that trace element is actually actively excluded from the carbonate lattice. So as a rough rule of thumb, aragonite with its orthorhombic structure is relatively generous and incorporates strontium more or less in the concentration it exists in seawater. I think if you took the strontium calcium ratio of average seawater, and if it was incorporated into carbonates in that proportion, then you'd probably end up with 6,000 or 7,000 ppm. So aragonite slightly favors the incorporation of strontium. So it's very strontium rich, but aragonite, of course, reverts to low magnesium calcite. If then that low magnesium calcite retains that high strontium, then of course that's a sign that recrystallization took place under closed conditions, and then therefore the strontium isotopic ratio could be preserved. Low magnesium calcite tends to be a lot less enriched in strontium, and that's because of its hexagonal structure. It actively discriminates against the incorporation of strontium. Dolomite even more so. So here's a few examples of those materials. So this is a study we did a long time ago for the Cambrian Ordovician boundary, and you can see that on the y-axis we're looking at very, very small deviations which is quite unusual for strontium isotope stratigraphy. So this is showing a genuine decrease across the Cambrian Ordovician boundary on a biozone basis. These are all conodon apatite values. However, we discovered that conodon apatite is only well preserved if the surrounding matrix is limestone, and that's because it will be buffered by the strontium isotopic composition of the surrounding matrix. Whereas if conodons are in mudstones, then they will incorporate radiogenic strontium from that matrix. And so conodons are not always well preserved, and that's because they do start off life as metastable hydroxyapatite. So the conditions of diagenesis are very, very important. There are also other studies. I'll just show very quickly the study where phosphate was used. And so where conditions were favorable, dolomite, phosphate, and limestone, bulk limestone, all gave comparable values. But the range of values here is nowhere near as small as the range on the left-hand side. I would also say with the conodons, there is a suspicion of very short-term heterogeneity. So maybe some cycles in here, which I'm sure reviewers would never believe, but I'll come back to that a little bit later. This is a great classic study by Adina Payton, who's been working on a series of barite samples for years and years with different proxies. And this is from some of those original studies where she compares forams and barite and shows that they are quite comparable, perhaps a systematic deviation from seawater, but very, very small indeed. And so if barite is precipitated from the open, in open marine conditions, then can also incorporate a seawater strontium isotopic value. And that's quite interesting because the strontium isotopic composition of barite in all its forms can then be used as a way of discriminating the source of that barite mineralization. Okay, all right, so now we're going to do a tag team effort, and Ying is going to take over my seat, and I will be back to join you in a few minutes.
Great. So Graham has talked about the materials we use analyze for strontium isotopes. And if we are thinking about the samples, and to analyze the 87/86 strontium ratio and aim to reconstruct a seawater strontium ratio when the rocks were formed, then we need to have to hold the principle in mind that rupture in and rupture out. So we need to learn about the samples over their diagenetic history and also the possible contamination. So with this, let's look at the published data. So this is our previous student, Helen Chen-Xi's work. So the aim of her PhD was to update the Precambrian strontium seawater strontium isotope curve. And when we reviewed of the published data of the Precambrian, we noticed that except for the age constraints, there are three related to today's topic aspect which will influence the strontium isotope ratio of the samples we'll look at. Firstly, if the samples are formed inside a marine environment, if they are well preserved, or which kind of, to what extent the sample undergoing diagenetic alteration, and also which kind of leaching method have we used. Okay, so we look at this four different aspects and come to evaluate the data which has been published from Archean into the Neoproterozoic. And here you can see that based on the four aspects, there are high certainty or high quality data until the low certainty data, then difference is quite large. This resulted in the updated data. What I want to draw your eyes to is this very green data point, which you cannot see very clear. These are all public data, but possibly not certain if it is come from marine environment or good preservation or leaching method. With this in mind, I want to remind you of the limitation of this, the samples, the rock samples we're going to use. Firstly, we need to look at the diagenesis also strontium systems is sensitive to salinity, and also there could be detrital contaminations, mostly rubidium, the radiogenic. So here is some examples of carbonate samples we're looking at. The first one is low magnesium calcite belemnite, and we can see well preserved, and also aragonite with ammonite with aragonite shells, and also low magnesium calcite from Nifra, and the poorly preserved samples. By comparison, we can see the difference. And Peyton also has shown the very beautifully with this diagram that the orthogenic precipitated marine barite, which is this tiny ABC, in this one's a tiny microcrystal from 1 to 5 micrometer in diameter of marine barite. And compared to hydrothermal barite, which is DEF, you can see it's quite morphologically quite different, and also the diagenetic barite. So they are not only differ from their isotopic composition. Obviously, this first three, the marine barite will be a representative of the seawater strontium isotope, but the other ones clearly morphologically also quite different. So we are now talking about the diagenesis. So what is diagenesis? Here I only go into, without going into too much detail, let's look at it. So basically is during the burial, when carbonate formed during burial, when they are exposed to diagenetic fluid, what will happen is during the wet dissolution and the reprecipitation process, that the minor and the trace element will try to substitute calcium cations in the calcium carbonate structure. So here, this whole process, the replacement, the substitution is determined by elemental partitioning coefficient K. Here is basically the equation shows how K is determined. Here I just show you the calcite to seawater system, how the K are of a few element are compiled here. So basically here, if K is over 1 or large than 1, or if the greater it is, which means it is easily during the diagenesis, the element will be easily to scavenge from the fluid into the solid. And on the if K is smaller than 1, which means that during diagenesis, the dissolution and reprecipitation reaction, that the element is easily to lose from the solid into the fluid, which will show in this diagenesis elemental changes theoretic diagram here. So basically, so simplified form, of course. So this is a carbonate equilibrate with seawater, and this is with meteoric water. We can see during the process of that the calcite or carbonate form already formed and exposed to the meteoric water, and what will happen is these elements will incline or will potentially lose from the carbonate, and these elements will increase, will gain more of this. Okay, so have that in our mind. We need to screen samples for the strontium isotope studies. So here I have compiled a few published cutoff and threshold. You can see that the cutoffs are quite different with the concentration of strontium and manganese, and the other also these other ones. And we can see for different samples we have quite different cutoffs. This, I think I want to remind you of what were available samples for most of the Earth's history is bulk samples, including, different type of the dolomitic, argillaceous, and the pure limestone, all sorts and biogenic ones. But we, for Precambrian, for example, we don't have biogenic fossils. What we have is bulk rock. So does bulk rock hold, it can be used as a good SIS proxies? So I have introduced you to two examples here. So Brand 2012 has looked at the brachiopods from the Carboniferous era, and we can see this calcedoluminescence photo from the fossil itself and the surrounding host rock, so bulk and with the biogenic material. And then to compare with modern brachiopods and their host rock. And what he has done is he gives a empirical or statistical range that the difference between the strontium isotopes ratios between the host rock and the fossil, and give a range that shows a lot of the host rocks can hold the original seawater signal. Similarly, I have looked at the molecular structure. So basically, molecular structure is more like the calcite. It's early diagenetic void fill of calcite microspar cement. Here you can see that the molecular structure CMC, and compared to its host rock, here the host rock and molecular structure, here again. So this structure basically is a low magnesium calcite with tiny grain sizes, microsporic, and this is under calcedoluminescence. And we can see that these rocks are normally tight packed and polyglow from 5 to 15 micrometer in diameter. I did the similar comparison of the strontium isotopes of the molecular structure and the host rocks. And we can see with the empirical range that Ulrich Brand has suggested, our large amount of the host rock I've looked at also give a similar strontium 87/86 ratio and compare to the molar structure. And I think this, after careful screening and the proper leaching method, bulk rock can also be a good seawater SIS proxy. So now we look at the screening and what kind of the diagenetic history of the sample we need to look at. So what kind of leaching method we need to use for our samples. Here is again, Helen has compiled existing dissolution methods for carbonate rocks. Here we can see we have a single leaching method with weak or strong acid without pre-leach or pre-wash, and we have two-step sequential leaching with pre-leach or without. And our conclusions are multiple steps of sequential leaching with pre-wash probably is the best, which most likely to obtain the better presentative strontium isotope value of carbonate. Okay, with this in mind, here I just show you two examples of the method, firstly, for quite pure carbonate, which means mostly low magnesium calcite, and it has developed mainly by Bailey, that's over 20 years ago now. And what they have shown with this graph is the after pre-wash, and the most rubidium and radiogenic strontium is already removed during the first step, the pre-wash. Okay, the exchangeable phase is out. And then they use weak acid. The step leach mostly is 5 to 6 steps to leach out all of the carbonate. And we can see from 30 to 40% to 60 to 70% that indicates they will leach out the pure carbonate phase, represents seawater value. And the oxide phases will come out later in the leach, and then we can see the final residue strontium radiogenic isotope ratio is indicated silicate. Okay, but as we have seen that most of the samples are bulk rocks, okay, and most of the bulk carbonate we can get is argillaceous and mostly dolomitic. So Helen, this is Helen now is a postdoc at Southampton. So we have choose in total 7 samples, but 5 of them are mostly argillaceous and a dolomitic sample. So compared with one pure limestone and one total dollar stone standard. So we can see the range of the carbonate content and the magnesium calcium ratio, manganese and the strontium ratio are quite vary, and we use 10-step sequential leaching, including the pre-wash using the pH neutral ammonium acetate. And each steps, of course, depending on the dolomitic content, we will have different reaction time. Here's some of the result. Here we can see on the the left side is carbonate content is basically slightly dolomitic carbonate, argillaceous. So we can see carbonate content from 57 to 75%. Magnesium calcium ratio is slightly low, so as high as 0.2. Manganese and strontium ratio is relatively low. And on the right side, we have argillaceous highly dolomitic carbonate, and which we can see the carbonate content is 62%, and the magnesium calcium ratio is as high as 0.4 and have much higher manganese strontium ratio. And what this result tells us is ammonium acetate pre-wash leached out the exchangeable phase, which has high strontium isotope value, and of course also the high rubidium and radiogenic strontium and other associated with the exchangeable elements. And the carbonate fraction of basically step 1 and step 2 and step 3, or both, the carbonate, we have yield the lowest strontium isotope ratio, and of course also lowest of the diagenetic or contaminate related element. And then after the step 2 or 3, and we can see the strontium isotope value, and the trace and major element content increase gradually each step after. So this is by comparison, use the same method for the pure carbonate. Here we can see is 90% of carbonate content with very low magnesium calcium ratio and very low manganese strontium ratio, with a very classic dollar stone standard. Here we can see is the pure dollar stone with the magnesium calcium ratio 0.6 and a very high manganese and strontium ratio. What this result tells us is, again, ammonium acetate wash did washed out the exchangeable phase quite nicely, and the carbonate fraction 10 to 70% roughly after the pre-wash, okay, yielded similar low the strontium isotope rate value from the low magnesium calcite, and you can see 70 to 100% carbonate leaching will have the lowest strontium ratio, but again, the 10 to 30 is actually not far behind. So when we look at this different leachates, we want to know if this carbonate is formed under a marine environment. Here we look at the rare earth element and neutron patterns and compare all 10 steps with the modern seawater pattern. Here we can see that step 1 and step 2 are most likely of most samples is quite similar to the modern seawater REY patterns. And the sample which is slightly different has a very high rubidium and a very content and a very low carbonate content. Okay, here again, this has been confirmed with the yttrium holmium ratio, which modern seawater is 36. Okay, of most samples, the first 2 steps, most of the sample are over this threshold. Okay, so what is brilliant with this is after we developed this, tested on the 7 samples, Helen has chosen 20 samples, and which covers the magnesium calcium ratio from near 0 to 0.6. 20 samples through the whole range and with different carbonate content. And we use all three very established method. So to compare of their result and the effectiveness of gaining the most representative seawater strontium isotope ratio. So here method one, so this blue triangle is this study targeted the first 10 to 30% after the ammonium acetate pre-wash. Method two is we use weak acetic acid to pre-leach 30%, and then the next 30% is being used for this for this value. And the method three is pre-leach 60 to 70%, and then targeting next 20%. Here we can see that the comparison shows that our new method not only can be used for pure carbonate or is higher carbonate content, lower magnesium and calcium ratio, but it can be very effectively leach out the carbonate proportion, for argillaceous and dolomitic carbonate for strontium isotope stratigraphy studies. And even if the carbonate content is as low as 40%, here we can still see is basically giving us a presumably the seawater range. So after the study, we also give a recommended, of course, cutoff threshold for samples which can use for SIS study. And we think from the previous study we have on strontium isotopes, a combination of the petrographic and the geochemical parameter will be important to screening the samples, and not only geochemical but also isotopic parameters. So all the data need to be looked thoroughly, and all of the recommended threshold, if the sample has a parameter higher than our recommended threshold, then they are less likely to retain the original seawater signal. And the carbonate content can be as low as 40%. We still can work with them for SIS. And also, of course, this is a case-by-case evaluation, and we do need to look into their own diagenetic trend and history. Okay, that's me, and Graham coming.
Yeah. Right, okay, so to cut a long story short, if you've got biogenic calcite and it's well preserved, you can blitz it with anything, even laser ablation. But most of us have to settle for dirty material or dolomitic material, but all hope is not lost. It just needs a lot more work to demonstrate, firstly, that there are diagenetic trends, and we know the directionality of those trends because strontium isotope ratios do tend to increase during diagenetic recrystallization, but that's just that's the dominant way. But it can also go the other direction as well if it's mixing with more unradiogenic fluids, which does happen as well. So it needs to be demonstrated on a case-by-case basis. So let's assume that we do get really nice strontium isotope values from samples. What is it good for? Well, I just summarize those as sort of 5 things. The first 4 are related to stratigraphy, really. Strontium isotope stratigraphy is useful for stratigraphic correlation. So 2 levels can be correlated together based on an identical strontium isotope ratio. Can also be used for geochronology, direct dating, identification of hiatuses, but also marine versus non-marine settings. And I also talked about that is quite important if you're thinking about the origin of mineralization, for example, for barytes. And finally, as a global weathering tracer. So let's look at a few of those examples. So this is again from the geological timescale book. And you can see that in these 2 sections, we have a horizon which has 2 values which constrain the seawater trend. So we've constrained that these are well-preserved samples at 0.7073, and then in the neighboring section 0.7073, sort of matches this part in the stratigraphy, and that is then one piece of evidence that we have now found a correlative level. And that's simply because seawater strontium is rising at that time. Of course, if it's not rising, or if it's only rising very slowly, then the resolution on that age correlation suffers. This is sort of what people did in this study. This is just one example of many we could choose. This is from the Permian, the Zechstein Sea, and so this is not carbonate so much as anhydrite and sulfate evaporite minerals, and you can see that the best preserved sulfate evaporite minerals. So here's the data on the left-hand side, and the seawater strontium isotope curve is on the right-hand side, and sort of the best preserved samples and the marine samples here can be constrained in age to between 257 and 254 million years. So this is using strontium isotopes for geochronology. So this would be the Stassfurt and the liner formations. But a lot of these data also are up in the sky, and these are presumably times when the connection to the open ocean was not so good. So this is one good thing that strontium isotopes can be used for. In evaporitic basins, it's very hard to determine the age sometimes, because they don't, because of the salinity, they often don't have correlative fauna, which can be used as biomarkers. And so strontium isotopes is frequently used to determine the age and also the relative openness of these restricted basins. As I said, strontium isotope ratios change over time. So they go up and down, and we can look at the rate of change over time, and that's what this is looking at. And the rate of change also can be expressed as a stratigraphic resolution. So when we have very high rate of change, then the stratigraphic resolution is potentially very good. But when not much is changing, it will be much lower. The other interesting thing about this plot is that if you look at longer timescales of 20 to 30 million years, the actual average rate of change, whether it's going up or down, doesn't matter, actually is pretty consistent at 26 times 10 to the minus 6 per million years. And that's an indication that the strontium concentration, and therefore the ocean residence time of strontium, has never been radically different from the current day. If you were to draw this back through the Neoproterozoic, I think you'd get a pretty similar picture. If you have enough data, you could even use this relationship to determine sedimentation rate in some basins, as long as we're talking about long time periods. You can also look at potential hiatuses or breaks or faults in a section, things which are cryptic disconformities, because if strontium isotope ratios are changing through time, then we would see a break in slope. If we know that the sedimentation rate is consistent and we still see changes over time, then that is something which is real, and it is part of the secular evolution of strontium isotope ratios. So they can be useful for that purpose as well. The other thing that you need to do, and we haven't talked about, is if rocks are old, then we need to think about rubidium decay. So carbonate minerals normally exclude rubidium, and that's a good thing. And if you use the ammonium acetate pre-wash that Ying was talking about, we can exclude much of the rubidium, but there will still be some residual rubidium. And if that rubidium strontium ratio is relatively elevated, then it could actually have a difference, make a difference in the final strontium isotope ratio, especially when we're talking about really old samples. So if you have a relatively low, or I should say high rubidium strontium ratio up here, then you don't need very old rocks before you start needing to make a decent correction of 1 times 10 to the minus 6. But if you have rocks which are Precambrian in age, of course, that rubidium correction will get bigger and bigger. So ideally, you want to avoid any kind of rubidium correction, because that assumes congruent dissolution of rubidium and strontium when you're doing your leaching, and that may not be the case. So getting rid of the rubidium in pre-leaches is absolutely essential. So finally, a lot of us are interested in how we can use strontium isotopes as a global weathering proxy. So this is where we will end up. Strontium isotopes or radiogenic strontium isotopes is one of many proxies that can be used for weathering. Due to its long residence time, it can look at globally integrated weathering rates, but it is a proportional parameter. Of course, it's relative to the input from mantle hydrothermal exchange. So they're always worth remembering this is a proportional parameter, and it can be used in conjunction with other isotopes like lithium, which is less dependent on the isotopic composition of the material undergoing weathering. So strontium will be dependent on that as well, obviously, because some materials will be more radiogenic than others. And then as we go down this list, we start to see heterogeneity from ocean basin to ocean basin, which we don't see with strontium. So just let's look at a few case studies from very small scale changes to large scale changes. So this is a very recent paper looking at the very rapid rise in seawater strontium isotopic ratio through the Oligocene. And the focus of this paper, similar to the Conodon paper earlier, are these tiny little glitches, tiny little kinks in this rise. So the strontium isotopic ratio may still be rising, but the rate of increase is actually significantly lower. And then it catches up with itself afterwards. And these authors suggest, by comparing it to delta 18 values, which are a proxy for ice sheet advance and ice sheet retreat, that these changes in the rate of slope are actually causing, they are related to these ice sheet changes. So there's a climatic influence on the weathering on this scale. And if this is a global phenomenon, then this is affecting globally integrated weathering rates, these climatic cycles. So that's actually quite exciting that we can see these very, very short-term changes. Mostly we can't. We're looking at a much longer term shifts, and that's because the reproducibility of our data is probably not good enough when we're dealing with bulk rock or much older samples. So this is a classic change in the ordovician, which was seen in conodonts, it's seen in brachiopods from Qing et al, and then in my own paper, 2003. But more recently, it's been extended over a much longer period here. So it looks like a more gradual kink. It was originally interpreted as the weathering of an unradiogenic source, presumably exposed igneous rocks, which would be unradiogenic, and perhaps the weatherability of those rocks would sequester carbon dioxide and would be one of the reasons that you lead into glaciation. The timing of that doesn't seem to work anymore, but maybe that's part of the story here. And that's part of the ambiguity of strontium isotope ratios, that even though we have a clear change at a clear moment in time, it's actually very difficult to know whether that is a decrease in weathering rate, whether it's a weathering of less radiogenic source, or whether there's something to do with seafloor spreading here. And it's very hard to tell the difference. If you look on, again, even longer timescales, so this is from Ying's work in the Neoproterozoic, and we can see that there are clear shifts downwards, which she correlates with the eruption of large igneous provinces, the most well-known being the Franklin igneous province, which again has been related to the onset of Sturtian or onset of glaciation. So before I was talking about the Hermantian, this is the Sturtian glaciation, and the timing in this case works pretty well. And so that there's the eruption of these easily weatherable basalts might input unradiogenic strontium into the ocean and also draw down CO2 at the same time. So there does seem to be some kind of relationship, at least on this scale. And when we look at it even longer scale, as we started with here, we have all sorts of different trends with different rates of change. This here at the end of the snowball Earth period, the very early Ediacaran, probably the most rapid rise in history, and that we know of, even more rapid than the Cenozoic. And this could be a combination of weathering rates and also sheer amount of material come into the ocean when we consider the desorption effect I was talking about earlier. And then looking at all of Earth history, and I think I've changed the age axis yet again, you see this is the most recent idea of how seawater changed. So this is from the work of Helen Shi Chen, and we can see this bit we know relatively well, but what she's been able to construct is at least our best idea of what happens earlier. So one thing to note here is the earlier deviation of the content of the seawater curve from the mantle input, which is suggesting that we have emergent continents quite early on. Okay, so it's not just about the continental crust evolution, it's also about whether those continental crust cratons are emergent or not. There's a possible reaction to the GOE here, so that could be related to acidic weathering after the GOE, will need to be confirmed. And then there's a relationship here, which is quite similar to the Gondwanaland orogeny here. This would be related to the formation of Nuna. But I would say that none of this is set in stone, but it's actually very interesting that we're starting to see some features, some detail in the strontium isotopic curve. What does it all mean? Well, I'm not going to spend very long on here, but people have noted over many years that there are covariations with other parameters, sulfur isotopes, carbon isotopes. In this case, there's a rough anti-covariation between strontium and carbon. That might be telling us something about that the tectonic uplift is actually determining both of these. So rather than this being related to just weathering rates per se, it is about the uplift of material, which is radiogenic. So this would be the cratonic interiors, which are uplifted due to collision. And that's bringing us radiogenic strontium into the ocean. And that has some bearing on these carbon isotope values as well. I talked about this in a paper and I won't go into in much more detail. What is supporting that is another anti-covariation between zircon hafnium isotopic values and strontium isotopic values. So seawater strontium is telling you about the dissolved load, whereas zircon is telling you about the material which is potentially available to be weathered. So it is suggesting that a large component of these first order changes is actually to do with the isotopic composition of what's being weathered, and not to do with weathering rates per se, which are tied to carbon dioxide outgassing. As Berner said, and he was there first as usual, 1994, when it comes to strontium isotopic changes, probably tectonic uplift and erosion is key. So in other words, physical weathering, and then chemical weathering rates is probably less important on these long time scales. And that's what this shows. And I'm not going to talk about this at all, but seeing it's on YouTube, people can have a look at it a little bit later. I was talking about this anti-covariation here between strontium and hafnium, and there you can see. So finally, we got there to the strontium isotopes as a global weathering proxy. There's a lot of uncertainties there. But there's also a lot of potential for the future now that we know how to get the best out of our samples. And I think I feel very confident that this curve will only get better and better. And with the combination of other proxies and also the zircon proxies that are coming out there, we can start to see what is actually the main governing factor over the strontium isotopic composition of seawater. If you're interested in going into any of these case studies, I would recommend looking at these papers. So this is the effective leaching paper that Ying was talking about, but there's also a few other papers here, for example, the emergence of the felsic crust in the Paleoarchean, and that's a barite related study, and et cetera, et cetera. Some of these I've mentioned in the talk already. What have we missed? Well, we've missed out loads of stuff, even though we've gone on for a long time. We've missed out stable isotopes. And the reason for that is that if you want to see the natural isotopic fractionation that occurs during processes, you actually can't use the data in the way it was produced for all of the data that I've been showing you. And that's because no matter whether you use TIMS, so thermal ionization mass spectrometry, or you use a multi-collector to determine 87, 86, we take a fixed ratio of 86 to 88 strontium to get rid of instrumental mass bias. And that means that we iron out any natural fractionation that may exist. So more recently, people have started to use the multi-collector, ICP-MS, to look at the stable isotope fractionation, but that involves using a double spike if you're using TIMS, or it uses sample standard bracketing or a zirconium standard if you're using multi-collector. And in the last couple of years, people have actually done a combination of both. And so you can get really high precision, 87, 86, and 88, 86 in terms of its natural variation. And so that's sort of what we're seeing here with one of Adina Payton's latest data. You can see part of the issue with stable strontium is that even though in the Cenozoic, we see such a lovely rise, systematic rise through the latter part of the Cenozoic. It's a bit of a messier picture when it comes to stable isotope fractionation. So it's early days for getting a lot of information out of that. But these records are getting better and better. But we didn't talk about that too much. And I think that probably should be the subject of another primer on a different day. So again, some more useful references for further background, and you can look at this as it will be preserved for posterity. And I'll just leave you now with the record that we started with. And I hope there was something there for everyone in terms of learning about strontium isotopes. So back to you, Eric.
Great. Thanks so much, Graham and Ying. I really appreciated that. I learned a ton, and it was really useful thinking about those sequential steps and how we might capture those in the SGP database in terms of preserving that important methodological detail. So why don't we open this? I'm going to turn we can all thank them for such a wonderful proxy primer, and I'll turn off the recording, and then we can get on to questions.